This week is a continuation and expansion on the topics from last week's lectures on ANOVA. A lot of the stuff we're going to be talking about isn't going to make sense unless you kind of picked up on the regression and ANOVA things that we talked about in the prior weeks. So what's the difference between ANOVA and factorial ANOVA? Well, nothing really. The formulas are the same, and the theory is the same. The only thing that is really different is the number of IVs, or independent variables, that you're interested in examining. So let's take a look at what that looks like in action. Let's get a little more in depth. In short, the main difference is that we compute separate model sums of squares for each variable. We calculate the deviations from the mean separately for each variable. And that is in figure 13.3 in your text in the 4th edition of the Andy Field book. If you look at the figure, you'll see that separate model sums of squares are calculated for variable A, variable B, and then their interaction as well. So this formula here should be pretty familiar by now. We subtract the mean for each level of a grouping variable. Okay, that's this mean for a group K. Okay, from the grand mean, we square the differences and then multiply it by the number of participants in that group, for that grouping variable. In this way, we have an estimate of how much of the deviation from the mean, the grand mean, is attributable to the manipulation. And the manipulation is indicated by the difference between the group means and the grand mean. The effect of a single independent variable or a single predictor variable is called a main effect. This is the effect of a predictor variable on an outcome variable. As we see here, this would be the main effect. This is how you would calculate the main effect for variable A. You would use these model sums of squares for variable A to calculate the main effect. If you remember from last week, there are also what are called interaction effects. And an interaction is when the effect of one predictor variable depends on the level of another predictor variable. To calculate the sum of squares for the interaction, we subtract the sum of squares for the main effects from the model sum of squares. So we have this model sum of squares, which is everything that we can attribute to all the manipulations. We subtract the individual main effects, and so then what's left over is the interaction effects, or those sums of squares, those model sums of squares that are attributable to the combined effect of the predictor variables on the outcome variable. Our hypothesis test, or our test of statistical significance, is the same as before. We divide the model sums of squares by their degrees of freedom to get the mean sums of squares, indicated here by the MS. Mean squares of the model, mean squares of the residuals. We divide the model sums of squares by their degrees of freedom to get the mean sums of squares, and then we divide the model mean squares by the residual mean squares to get the F ratio. Same as before. In this regard, separate Fs are calculated for each main effect and for the interaction effect. So if you had two variables, you'd have three F ratios. You'd have one for the first variable, an F for the second variable, and then another F for the interaction. In the event of a significant interaction effect, main effects are not to be interpreted or discussed. Just ignore them. Only interpret and or discuss the interaction effects. You may see papers that discuss or interpret the main effects, and they're just wrong. In fact, there may be papers you read that do a few of the statistical no-nos we've talked about. They're wrong too, and it's unfortunate that someone didn't correct them before being published, but statistics is difficult and complicated, and it's often the case that people do it wrong or misinterpret things or are misinformed about a specific statistical test or whatever. So you will see these errors made, but it's important for you to know that if you do run statistical tests and you get an interaction, only interpret the interaction. Do not interpret the main effects. Oops. Where are we here? With between subjects ANOVA, there was an assumption that data was independent. That is to say, one score was independent from another score. However, in repeated measures ANOVA, we're interested in the change or differences across time. In this case, scores are dependent on one another. Two scores are coming from the same person at different times. These scores would be called dependent. They came from the same person. They're dependent on one another. They're dependent on the person that they came from. Therefore, we have to do things a little differently when we calculate repeated measures ANOVA than a between subjects ANOVA. With the repeated measures ANOVA, we're interested in the effect of an experimental manipulation within subjects. In a between subjects design, the differences between participants aren't accounted for at all. But in repeated measures design, we are interested in how much of the individual differences are accounted for by the experiment. In the between subjects design, the individual differences were considered to be error. We didn't analyze them or examine them at all. But with the repeated measures ANOVA, we're gonna pull that apart a little bit more. We're interested in how the manipulation affects a difference within an individual. One statistical assumption we haven't yet discussed is sphericity, and this is important for repeated measures ANOVA. Sphericity is the assumption that the variance of the differences between conditions is similar. And this is similar conceptually to the assumption of homogeneity of variance or homoscedasticity that we talked about earlier in the course. Okay, the variance of the difference between time 1 and time 2 should be similar to the variance of the difference between time 2 and time 3. Okay, that's what we're talking about when we're talking about sphericity. You can only have sphericity if you've got, or sphericity is only an issue when there are at least 3 measurement occasions. You can't really test sphericity with 2 measurement occasions because all you're looking at there is the variance of one difference score, the difference between time 1 and time 2, and there's nothing to compare that to. There's just no comparison to compare those variants of the differences to say that they're different or the variance is similar or different. Now, if you do have 3 measurement occasions, we can test the sphericity of that data by computing Moakley's tests. And Moakley's tests ask, are some conditions more dependent than others, or are the variance of differences between conditions different? When Moakley's test is significant, it means that the variance of differences between conditions is different, and the assumption of sphericity has in that case been violated. However, it's important to note that with large sample sizes, this violation is actually can be more likely to be violated even when the variance of differences between conditions is small. So if you have a large sample size, your data may actually be the variance of differences may be pretty similar between conditions, but the Moakley's test may be significant anyways, just because with more subjects you don't need as much of a difference for it to be significant. It's easier to detect a difference. So there are several corrections for violation of sphericity, and they're discussed in the text. I'm not going to go into details. Just know that sphericity is an assumption of repeated measures designs, and that when violated, a statistical correction should be applied. Some of the ones talked about in the book are the Greenhouse-Geyser correction or the Hohenfeld correction. I know the Greenhouse-Geyser is used a lot. Does a pretty good job, it seems. But you don't need to know all the details. Just know what sphericity is and why it's important. So how do we calculate the sums of squares for repeated measures ANOVA? Well, just like our between subject statistics, we calculate sums of squares. In this way, our F ratio is going to be the ratio of deviations explained by individual differences attributable to our manipulation divided by the deviations in individual differences that are unexplained. So, what can we explain about the change within a person using our model? Relative to the change within a person over time that can't be explained to our model. That's what the F ratio is going to indicate. So the total sum of squares is calculated the same as before. We multiply the grand variance by the degrees of freedom. It's pretty simple. Our model sum of squares is also like before. We calculate the deviation between the mean for a condition and the grand mean. Okay, so in this case, the conditions aren't between subjects conditions, the conditions are times. Okay, so time 1, time 2, time 3. We calculate the sum of squares within, okay, this is SSW, this is new, by summing the variance for each participant's scores. In this way, we have an estimate of individual differences that we didn't have with the between subject statistics. This is kind of like the residual sum of squares we computed for between subjects ANOVA, but we sum the residuals over subjects. And that sounds like that's a mouthful, but it may make more sense if you go back and read through your text and then listen to this again. It also may help to go back and look at how the residual sum of squares were computed for the between subjects design. You can compare that to the repeated measures. The main difference for repeated measures is in the calculation of the residuals. The residuals here are the individual differences that aren't accounted for by the differences due to condition. The F ratio is calculated the same as before using the sums of squares averaged by the degrees of freedom. If you're lost at this point, don't fret. There's some additional support on YouTube again, actually from our text author, Andy Field. So I'm going to be posting a link onto D2L of Andy lecturing on repeated measures ANOVA. It's kind of a long, it's a bit of a long lecture. I think it's an hour or 90 minutes or something like that. But if you really wanted to get into it, you could check that out. There are probably other good resources out there too. I didn't find one from Salman Khan on repeated measures ANOVA, but there may still be one available, or another one from somebody who's also would explain this well, or could provide you kind of additional support. Mixed design ANOVA. We didn't assign this in any readings for mixed design ANOVA, or I didn't assign any readings for mixed design ANOVA because the calculations are essentially the same, and Andy talks about that in the text, but he doesn't really go much into the rationale behind it, because we've already talked about the rationale, the theory, sums of squares, F ratios. We've already talked about all that. It's essentially the same. Mixed design ANOVA is also known as split plot ANOVA, or between within ANOVA, or mixed ANOVA. And it's essentially when we examine both between subjects and within subjects factors in the same ANOVA. It's the same as before. We also compute the between subjects sum of squares, just like with factorial ANOVA. So now we're computing F's for the between subjects effects using between subjects model sum of squares, and we're also computing F's for the within subjects effects using within model sum of squares. In a mixed design, we can also have interactions between within subjects and between subjects factors. So this interaction is interpreted just like before. The outcome variable is dependent on the effect of another factor, another outcome variable. Okay, for example, a drug had an effect greater than placebo, but only 2 hours after ingestion. At 8 hours, the effect was similar between drug and placebo. That would be an example of a between